Now, first of all, what was the need? What was the need? If we are still in real numbers, what was the need of this new definition? Okay, so like if we have a function like f of x equals to some function like x squared plus 3x. So I have a variable x and I'll get an answer, right? So basically function in one function is what? What is a function? Function is a machine that has an input and that has an output. So what can be the input of the machine is actually the domain, and what is the output of the machine is actually the range.
Yes.
This is the domain. This is a one variable function. But when you draw a graph of one variable function, you need a two-dimensional figure.
Yes.
Why? Because you have two things. You have a domain, you have a range. Domain is represented on the x-axis and y is on the range is on the y-axis. Right?
So y represents the range and x the domain, right?
Yes. Y represents the range and x represent the domain. So in one variable function, we are here in two-dimensional. So what do we do is, like, if I have a function, let's say this is the function, this is the graph of a function. If I want to check whether at point A, the function is continuous or not, the first of all thing is like that A should be from the domain itself. Right? That's why I have taken this A point on x-axis. Right? So the earlier definition was something like, if we are approaching x toward left hand side. Let me get the graph. Yeah. So if I'm approaching my x from the left hand side, what is the value of x? Means I'm here. So let me check the value of the function. So value of the function.
Your voice is cracking a little bit.
Hello?
Yeah.
Yeah, okay. Yeah. So we are here on this point. So let me just check what is the value of x. Now I'm approaching toward A. Now my value of the function is here.
Yes.
Again, I'm approaching toward A. The value of the function is here. So I can see my value of the function is approaching toward f of A.
Yes.
Right. Similarly, if from the right hand side, I'm approaching toward A. So in the right hand side, I have to see where my function is approaching. The range is approaching. So right now I can't give a direction, but as soon as I get into another arrow, I know that my function is now decreasing here. Right? And it goes like that. And we say that both the limits, from the left hand side, from the right hand side, it approaches to f of A. So that's why the function is continuous. Yeah.
Yes.
This definition, now this was the earlier definition, but what happens in the higher dimension? That's where the question of this definition arises. This definition cannot be applied if we are in higher dimension. I'm not talking about like 4 or 5 dimension. Let's just move it to one more dimension, 3D. Okay. So in 3D, what would happen? Say f of xy is x square plus y square.
Yes.
Here, the function is of 2 variable. That's why the graph would be in 3 variable.
Yes.
3D. So if this is my x, this is my y, this is my xy plane. Okay.
Yeah.
So I'm putting the value x comma y. So my whole xy plane is now domain.
Right.
And again, this would be a number. This would be just a number. This is not a coordinate. This is not a in some R2 or R3. This is just a number. This is a real number. Right. And this real number I'll represent on Z. So the range is on Z, but the domain is on whole XY plane. Got it?
Right.
Okay. Yeah. So let's say if I have a point, acha, like I don't know what is the graph of x square plus y square, but let's say I have a curve, something like this.
Right.
Right, I have a curve like this in the 2D. Now every a comma b in the xy correspond to a point on that surface, and that you'll draw a perpendicular toward the z-axis and you'll get the range.
Right.
This is how it works. But see here, domain was represented on this line. If I have a point on it, there are only two ways. There are only two ways to approach this point. Being
Yes.
the domain itself means we have to restrict ourselves in the domain. We can't go outside the domain, and we have to reach toward A.
Yes.
So this is the A. This is the left hand side. This is the right hand side. But see here, this
Yes.
whole is my domain.
Yes.
For reaching toward A comma B, I can choose this path. This is not a
Yes.
left hand limit or right hand limit.
Yes.
Right? I can choose any other path or a straight line or anything on the XY plane. Right?
Yes.
So the path actually matters. In R1, actually the path is only like two directional paths. We are just dealing with 2D. We are just dealing with a line. A line is a one, like this line is one dimensional. Point is a one dimensional, right?
Yes.
So we can approach from left or from right. Only two options. But here the picture changes. And it will now give me another definition. I now want another definition of domain. Of what? Neighborhood.
Yes.
Right? Just a second. Yeah. So now I need to define a definition of the domain, that a neighborhood that can be extended to the higher dimensions.
Yes.
Okay. So I need the definition of a neighborhood. See, in 2D, I can give a like intuitive way to understand the things. Okay. Similarly, in the 3D, I can give you an intuitive idea. But now theory has to continue. Now the intuition stops, right? In the 4D,
Yes.
the 5D. Okay. So that's why we have to change the definition of the continuity, and that's where epsilon delta comes into the picture. Is that clear?
Yes.
Oh, great. Now, I'm drawing a function which at point A is continuous,
Yes.
and a function which at a point A is not continuous.
Yes.
This is not continuous at A.
Yes.
Can you apply the definition and tell me that with the epsilon delta definition, can you tell me, like, yeah, it is clear that for epsilon we can't find a delta in the second part, and we can find in the first part. Like f of A is defined, okay? F of A is defined in
Yes.
Okay.
Yes.
So what we need to choose first, like epsilon or delta?
Epsilon.
Epsilon. Epsilon is around f of A or A?
It will be around A.
For, this is like for epsilon greater than 0, given
Yes.
f of A minus f of x, sorry, f of x minus f of A is less than epsilon for all x minus a less than delta.
Right. Okay.
Right. So whenever I choose an epsilon, first of all, I'll have to choose an epsilon. Okay. Once an
Yes.
epsilon is fixed, I'll make a epsilon neighborhood around f of a.
Okay. How do we determine what value of epsilon to give and how exactly to make the neighborhood?
Yeah. The definition says if whatever lambda you give me, I can choose a delta for that. That's continuity.
Right.
If there
Right.
exists even one delta for which you cannot give me a delta, epsilon for which you cannot give me a delta, the function is not continuous at that point. And I'll show you that epsilon over here because this is not continuous.
Right.
Yeah. So let's say if I choose an epsilon of length this much. Okay. This is basically f of a minus epsilon. This is f of a plus epsilon. So these are the values. Okay, I have chosen. Now it says I have given you an epsilon. Now you give me a delta around a.
Right.
Right?
Yes.
It should be like just a second. It should be for epsilon greater than 0 given there exists a delta greater than 0 such that. So now you'll have to find a delta. Okay, let's find a delta. Now, if I assume this to be a delta, this length to be a delta, so my neighborhood is a minus delta, a plus delta. Okay. Now you find out the value of these elements under this function. Under this function, it would be
a plus delta and a minus delta, like within.
Yeah. So the all the values are within this neighborhood.
Yes.
That means I have found a delta.
Yes.
That means, see, what does x minus 3 less than, let's say, 1 means? What does that mean? It contains actually all the points such that the distance from the x from 3. So first you draw 3. So from 3, the distance cannot be greater than 1.
Yes.
Right? So you cannot go beyond 4.
Right.
And you cannot jump this 2. So basically all the x are from here. So that's what it says, that whenever you choose your x within this, your answer should be within this.
Right.
Okay. So of
but
course,
then it's lesser than positive 1, right? So can't we take other numbers like say 1?
In like what?
Okay, no, it's a modulus function, right? Okay, no, then it will only between 2 to 4.
Okay.
Got it.
And actually, your delta will depend always depend on the epsilon that you're given. Okay.
Right. If it was just x minus 3 lesser than 1.
X minus 3 lesser than 1. So that means your like a is fixed, and there must be some epsilon corresponding to which you are giving me a delta.
Right.
Okay. So see, first epsilon is given, you find a delta, but then the story is other way around. Then you find a x from here and you check whether this x is within this neighborhood or not. That's what we call the definition. That's when we say that the definition is satisfied.
Right.
Okay. Again, see here. I want to draw an epsilon neighborhood around f of x. So let's say So let me take the epsilon as this neighborhood.
Right.
This is the epsilon I have taken. So for that, you need a delta. Okay. So let me see, this is my delta. Right. So this is a minus delta, a plus delta. Tell me all the values from this domain is under this range or not?
Yes.
So basically,
Like in the range.
yeah. So what you can do is like, you can do simply this, and this is all the values. Of course, this is within this neighborhood. So I'll say that.
Yes.
So I'll say that for your given epsilon, I have found a delta such that this happens. But it doesn't imply
Yes.
the continuity, because continuity is for every
Like this should.
epsilon given.
Yes. Yes.
Okay.
Also, like it's visible from the graph that it's not continuous.
Yeah. No. Yeah, of course, it is not continuous. But I'm giving you an idea because the situation where the graph is not so obvious, right?
Right.
Right. But still, can you think of an epsilon here for which we can't find a delta? Because this is see, that's what you said. From the graph, it is quite clear that it is not continuous. So that means you
Yes.
must give me an epsilon for which I will not be able to give you a delta. What would that epsilon be? I can make any epsilon. Take this epsilon.
Yes. Yes.
Now you cannot tell me any delta you like, whatever delta you choose, whatever, howsoever small, it would not be within this epsilon neighborhood.
Right.
Right? Because see, like no matter how small you take, this will go beyond the neighborhood.
Yes.
Right? So for one epsilon, if you're finding that delta, it doesn't imply that for every epsilon you'll be able to find it, right?
Right.
So
So exactly what is the relation between epsilon and delta?
for epsilon, here for epsilon means you have to find a neighborhood around f of a.
No, that's absolutely
Yeah.
fine. Like, but what's the like relation between epsilon and delta?
Relation,
How are they related?
they are directly dependent.
No, as in like, is there any fixed formula?
No.
Delta will be smaller or anything.
No. It will all will always be changing with respect to the function they have given, with respect to the point they have given. There's no relation. There's no fixed relation.
Huh.
Okay. So see, what I'm trying to say is here, if you in a question, if you are trying to prove a function to be continuous, you will try to find, see, epsilon will always be given. So you'll try to find your delta as a function of epsilon.
Yes.
Right? Like you are giving me an epsilon 0.1 and I'm giving you an delta like 0.01. So I'll say, yeah, for your epsilon, this is your delta and you can satisfy. Now you comes up with another epsilon. Yes. I'll give you another delta. Now I want to give you a delta in terms of your epsilon. Like I have given you a delta. This is like, if I have given you a delta epsilon by 2. Now you don't ask me if I have given you 0.1, what would be the delta? I have given you a delta in terms of epsilon.
Yes.
Okay. So most of the time what we do is, if you're trying to prove a function to be continuous with this epsilon delta definition, you always try to find your delta with respect to epsilon.
Yes.
As a function. Okay. And here in this case, what you can do is you can find one epsilon such that for that epsilon no delta exists.
Right.
Right. But this is sometimes difficult for not continuity. For not continuity, this is sometimes difficult. So we use the sequential criteria. Okay. I'm not going to the proof, like why this is happening. I'm just telling you first of all the definition. What is the sequential criteria? Sequential criteria says, like, if this is a point A, okay, and you find a sequence
Yes.
right? You find a sequence that converge to your A, then
Yes.
f of x also converges to f of A, will implies that function is continuous at A. This is the definition.
Yes.
So in sequential criteria, I want to check my function continuity
Yes.
of function at x equals to A. So what I'll do, let xn converges to A, and like if for all xn such that xn converges to A, f of
Yes.
xn converges to f of A, we say f is continuous at x equals to A, right?
Yes.
There is a definite problem here. What is the problem? The problem is this symbol.
Yes.
Like if I want to show my function is continuous at some point, I cannot consider every sequence in the world which converges to A. Of course, there will be, you know, the concept of countable, uncountable.
Yes.
Okay, so there will be uncountable number of sequences,
Yes.
right? I cannot like go one by one. So
Yes.
what we do in the questions, we actually take a random sequence that converges to it. You can also make a random sequence. You can also, I'll tell you how to do that. But basically this sequential criteria is not so useful in proving the function is continuous.
Right.
Right? If I can't find a general sequence, otherwise it is easy. If I can't find a general sequence, this is not a good idea to use the definition. Contrapositive is our concern in sequential criteria, because if there exists even a single sequence such that these two conditions are not satisfying, that means f is not continuous. Simple.
Yes.
So basically you have to find either a general sequence which satisfy these two conditions, or a sequence that does not satisfy these conditions.
Yes.
Okay, let's jump to a question. Let's do Dirichlet function. Heard about it?
Yes.
Okay. Where the function was something like actually before that, do you know, tell me something about this function. What was the function? Greatest integer function.
Uh, like the definition of the function.
Let me just a second. Greatest integer function. What is greatest integer of 2?
For integer of 2 will be 2.
0.1.
0.1 will be 0.
Okay, fine. So you know about this. Now Dirichlet function. Dirichlet function is 1, 0. Let's say x belongs to rationals and x belongs to irrational.
Yes.
Okay. Also, there's a very it's you can say a contradictory point in every book that you'll see. What is the definition of rational function?
Definition of a rational function.
No, not rational. Just rational number. Tell me what is rational number. I want to write rationals as a set.
Okay. So, like, basically, rational numbers. We had a form for it, but
Yeah. Tell me the form.
P by Q.
P by Q. Now some restrictions on P and Q.
Q not equal to 0.
Q not equal to 0. Anything else?
There were more.
Like Q and M should be integers, first of all. Okay. I can't write root 2 by 1.
Right. Right.
They both should be integers, first of all. So right. P and Q belongs to integers. Right? Also, right. Is a condition. So I'll write it in the point so that you remember actually. such that number one, Q, P and Q, they both belongs to integers. Number two, Q is not equal to 0. Number three, P and Q, GCD of P and Q is 1,
Right.
right? And fourth, which is very important when we use these kind of things, when we actually use to distinguish the nature of a function different on the rationals and totally different from the irrationals. This point should not be missed, that 0 is actually, we will consider 0 as 0 by 1. Because see,
Okay.
if I'm
P by
taking
Q.
this as 1 by n, is that a function?
Yes.
Okay. But f of 0 is actually f of 0 by 1, which is actually 1 by 1, which is actually 1.
Yeah.
But f of 0 is actually also f of 0 by 2. In that case, it will be 0 by 2. So basically, function is taking 0 to 2 points, 1 and 1 by 2, which is not a function definitely.
Right.
Right. So if I'm specifying this, so the definitions has to contain these all points, and Bartle in the very beginning, he specifies it. Like whenever rational is used, this is done. Okay. So, so 0 can only be written as 0 by 1 when I'm considering a function.
Right.
So these are the 4 points. Now, Acha, tell me, is it a continuous function, discontinuous function? What do you know about this function?
About Dirichlet function. Okay, there was something unique about the Dirichlet function and continuity. Like it was an exception.
Okay. So basically, see, whenever we talk about the continuity is always discussed on a point in the domain, right?
Yeah.
But if I'm talking about it on a set, that means if I'm telling that this function is continuous on the domain 0 to 1, so what I'm trying to say,
it wasn't continuous. Like
sorry,
the Dirichlet function. The Dirichlet function.
The Dirichlet function is not continuous?
No, but it had some exception.
Okay. No, in this particular, in this only this particular function, is it continuous on any point?
I do not. I'm not sure.
Okay. Let's see. Let me consider this function here. So first of all, of course, the domain is all real. So I can discuss the continuity on all reals.
Right.
I can discuss the continuity at every point in the domain, and the domain is all real, so I can discuss. So let's say, let A belongs to rational.
Right.
Okay. So what I'm doing is I am dividing my domain into the 2 parts, rational and irrational. I'll take a point on rational, an arbitrary point, no restriction on it. If I'll be able to show that my function is continuous on this A, that means it is continuous on every point of Q.
Yes.
So I'll say that the function is continuous on every point of rational.
Right.
Right. So let's see what is the result given me. Now, for this, what was our approach? Sequential criteria says you find a sequence converging to this.
Right.
Okay. So I'll find a irrational sequence converging to it. So consider Xn belongs to irrational such that Xn converges to A as n tends to infinity. What is the reason why I'm always able to find an irrational sequence that converges to a rational number?
Why?
Yeah. What is the reason? Like, is it always possible? Like I'm telling you a rational number 2 by 3. You tell me a sequence of
2 by 3.
You tell me a sequence whose all the numbers are irrational and still converges to 2 by 3.
Okay.
Acha, what is this limit? Have you done sequence in series? Hello? Can you hear me? Hello? Can you hear me, Trisha? No, bacha, I cannot hear you. You can try to leave and rejoin. Sometime happens.
Yes, ma'am. So
Yeah. So what is the limit?
of 1 plus 1 by n to the power n.
Yeah.
It will be the e, right?
Yeah, it should be E, yes. E is an irrational number.
Yes.
Every point in the sequence is irrational.
Right.
So what I'm trying to say that it can happen, right?
But can it like approach 2 by 3?
Yeah, of course. Of course, like you see, that's what I said. You have to find either a general sequence or
Right.
you have to find a sequence that doesn't satisfy. I'll find a general sequence here that will not satisfy my that condition. So it will not be continuous basically. So, 2 by 3, for 2 by 3, this is a rational. See, here it was the other way around. It was irrational, but here it was rational, right? I want an irrational sequence converging to 2 by 3.
Right.
The simple one, this is the simple one. Like you take 2 by 3 plus root 2 by n.
Plus root 2 by n, okay?
Limit n tends to infinity. It would be 2 by 3.
Yeah.
But
yeah.
Every term is irrational.
Irrational.
Okay. So even you can make a general sequence here.
Yes.
Consider this belongs to IRN such that this. So if you don't want to give a reason for it, like why every time it is possible, it comes from some denseness property, denseness of irrationals in reals. Remember?
Yes.
There are 2-3 proof of these two lines. You can use the denseness theorem. You can do it by that just a second. Limit point.
Right.
This derived set of have you done this terms derived set, interior sets, cluster point?
Cluster point, yes. Interior also, yes. Not derived sets.
Not derived set. Set of what limit point is derived set. Have you done that? Set of limit points.
we've done limit points, but set of all limit points, like also we've done, we just weren't given the term derived.
Oh, okay. Yeah. So yeah, that will also be, that can also be considered here. So okay. But if you don't want to give the reason, you will find a actual sequence. And for that sequence, you can just make either this, or you can see, consider a plus root 2 by n. That will belongs to irrational.
Yes.
Limit a plus root 2 by n is equal to a.
Right.
So actually you have found a sequence that is converging to a random number from rational that you have considered, an arbitrary number.
Yes.
Let's see what happens in f of xn and f of a. So f of xn, now f of xn is actually f of 2 plus a plus root 2 by n. What it would be?
Yes. So the elements will all be irrational.
These elements are all irrational.
Yes.
What is the value of the function for x irrational?
0.
It would be 0.
Yeah.
So, and what is f of a?
F of a. Yeah, it will be 1.
It would be 1. So
Yes.
if function is continuous, then this limit is converging to a. F of xn should also converge to f of a.
Yes.
But you see, but limit n tends to infinity, f of xn is equal to 0,
Yes.
because every element is 0.
Yes.
It cannot be equal to f of a, which is equals to 1.
Yes.
Therefore, by contrapositive of sequential criteria on limits, fx is not continuous for all
Yes.
x belongs to rationals.
All right.
So if you have used this as little like you can see, like this will always happen because of the denseness property, or because that limit point. If you don't, you have actually found the sequence.
Right.
Okay, so either of them you can do. Acha. For the other one, see, the whole story will be same. You try this one. Let B belongs to, I'm writing all in green color, like for B belongs to irrational.
Yes.
Acha. Now the problem would be this. Let B belongs to irrational. Acha, let me tell you a trick for this. Okay, don't write it in the exam. Like you don't have to show it on the answer sheet.
Okay.
Whenever you come across with these kind of functions, what you'll do, you'll equate these two.
Okay.
1 is equal to 0. Is it true at any point of x? No.
No.
So the function is not continuous at any point, first of all.
Right.
So if the function would have been something like x and x minus 1, when x belongs to rational and x belongs to irrational. So basically x equals to x minus 1. Is that true for any x?
No.
Again, not continuous. If like x is equal to 2x minus 1. Let me consider a point. This is so if it would have been x into x minus 1, x belongs to rationals, x belongs to irrational. So it is x equals to 2x minus 1. What is the value of x for this?
Yes.
X
Plus
is equal to
1.
1.
F of x
So,
will be 1.
yeah, f of x is equal to 1. So actually, before starting the question, you actually know at what point this function is continuous.
Right.
Okay, so you'll be careful while proving that you'll like choose A belongs to rational except one.
Right.
Except one, because you know at one it will be continuous, so it will create some problem if I won't exclude my one here.
Right.
Okay, you can follow the same proof otherwise. So here it in the question that I have taken, it is not continuous at every point, at any point. So, so what I'll do is let B belongs to irrational. Let B belongs to
Yes.
irrational. Acha, now I have to consider this. Okay, so also, Tisha, this is something that you can memorize. Actually, you may have to find this kind of sequence
Okay.
approaching to a rational number. Like you have, if they say any rational number, you have a sequence of irrational number converging to that rational number.
Yes, we've done something like this in past.
Okay, that's fine. Okay, now the other way around. Now you have to find a sequence in rational that converges to.
Yes.
So consider any idea, anything that you can think of.
Not separately, no.
Okay. Acha, or let's pick up a irrational number pi.
Okay, fine.
Okay. So let us try to find it in not in a more general sense. Let us try to find it in some random irrational number first. Let pi belongs to irrational. So I'm
Yes.
trying to find a sequence that converges to pi, and every term of the sequence should be rational.
Yes.
So, approximately, tell me how many digit you know. 3.14.
1, 4. I think the next are 2 and 8.
1 for 1.
Not very
Yeah.
Okay. No,
Okay, so we'll do. Yeah, this would be enough. This would be enough to understand. See, what I'm trying to generate, a sequence whose first number, like first element would be 1. Next number would be 3.1. Next number would be 3.14. Next number would be 3.141. These all are rational.
Yes.
All are rational, and continuing in this manner, it will converge to my pi. Okay.
Yes.
I cannot do that in general sense. Right. So I need a more general idea here. I have to use pi, not the value of pi.
Yes.
Okay. So because I have B, I don't have the value of B.
Right.
Right. So here, what would be pi, greatest integer of pi?
3.
3. First element is obtained.
Yes.
What would be the greatest integer of 10 pi divided by 10?
Pi divided by 10, that will also be 3. Right?
What is the numerator first of all?
10 pi.
The actual value, like 10 pi, the greatest integer of 10 pi. What is the
Greatest integer of 10 pi will be 31.
31. And 31 by 10 would be?
3.1. Greatest integer will be 3.
Second term is obtained?
Yes.
You're trying to understand what I'm doing. I'm just shifting a point there and I'm collecting that number, and then I'm giving it a point so that it makes a rational number.
Yes.
Okay.
Yes.
Again, 100 pi would be 100 pi.
100 pi.
Greatest integer of 100
yes.
pi.
Greatest integer of 100 pi would be Okay, let's see. Greatest integer of 100 by, it will be same. Greatest,
100 pi means the point is shifted toward here,
yes.
and the greatest integer means,
Like the floor value of the function.
yeah, so 3.314
3.4, yes.
divided by 100, it would be
3.4 divided by 100.
Yeah.
It will be mm, so it will be 3.14.
Yeah, 3.14, and that is my third term.
Yes.
Getting my point? In this way, I can actually generate a sequence whose every term is a rational and the sequence itself converges to an irrational number.
Right. Right.
Right. So the general, and I haven't used the value of pi. I'm actually using pi everywhere.
Right.
Right. So the sequence that I can make here is actually greatest integer of b, greatest integer
Yes.
of 10 pi, sorry, 10, not 10, 10b upon 10, 10 square
Yes.
b upon 10 square, and so on. So the sequence I'm considering is 10 to the power n minus 1 b greatest integer and upon 10 to the power n minus 1. This is a sequence of rational terms converging to b.
Yes.
Now all I have to take care about f of this and f of b.
Right.
Okay. So for both the cases, you have the general sequence now.
Yes.
Now let's talk about f of this term. F of
Yes.
this. This is definitely a rational number.
Yes.
For rational number, my function is
1.
1. So this is actually, there is a difference between convergence and equals to. This does not converge to 1. This is actually 1.
Oh, just equal to 1.
Just equal to 1 for all n belongs to natural.
Right.
Right. So every term of the sequence is 1. Not like the term, the sequence is converging toward 1. If every term of the sequence is 1, it is converging to 1.
Right.
Right. Okay. So, and what about f of b? And f of b. B is irrational. For irrational, it is 0.
B is irrational, so 0.
0. It implies f of 10 to the power n minus 1 b upon 10 to the power n minus 1 is equal to 1. It does not converge to f of b that is equal to 0.
Right.
Therefore, function is not continuous for all b belongs to irrational. So combining the first and second statement, we can say it is not convergent on any real number. It is not convergent on any, not convergent, it is not continuous on any rational, it is not continuous on any irrational, there is not continuous on any point of real number.
Right.
Okay, so this was the basic idea on how you can use the sequential criteria to not prove the continuity.
Right.
Okay, to not prove the continuity. Let's have one more example here. Popcorn function, heard about it? Thermo function. There are so many names for it. The function is this.
Right.
Function is, let's say, what was the function? 0 when x belongs to irrational.
Yes.
And 1 by n when x is actually m by n belongs to rational. Given this m, this rational that I'm choosing, that satisfy all the points of the definition. Okay.
Yes.
All these 4 points.
Yes.
So f of 0 would be 1. Okay, fine. So this is sometimes also known as popcorn function, or this is known as Fermi function. There are also so many names for the function, but you just know. Okay. Now, acha, the shortcut I have told you to check the point. This is a shortcut. Shortcut always has a flaw. It
Right.
may or may not work. Okay.
Right.
Here it won't work. 1
Yeah.
by n, can it ever be equal to 0 for any n?
No.
Never. But still it is continuous at some points. We will just find out
Yes.
at those points.
Right.
Acha, so if I follow these theory, this rational, take a rational and a sequence and everything. So what would be the problem here? So first of all, let's start with the rational. Let A belongs to rational. Then
Right.
A plus root 2 by n belongs to irrational for all n, belongs to natural.
Right. Yeah.
And it also converges to A as n tends to infinity, right?
Yeah.
So in the similar manner, if we apply the f here, now f of A plus root 2 by n, that means f of irrational. F of irrational is 0. So this is equals to 0. And f of A. Now see, I don't know what is A, but I know that A is actually some rational number whose denominator is non-zero.
Yeah.
So it implies f of A has to be some 1 by n. I don't know, like
Yeah.
it can be p by q, so it is p actually 1 by q.
Right.
Right. So you'll write for some n belongs to natural. So let's see. Let me have a change here. P belongs to integer, and let's say Q belongs to integer. Okay. So basically, what I'm doing is I'm taking all the minus to the upper side. Like I'm not considering 1 by minus 2 anyway. It is for
Right.
me, it is minus 1 by 2.
Yeah.
Okay. So for some natural number, this.
Yeah.
So this would be 0, I guess, right? So it's 0, no? For irrational, it is 0, no?
Yes.
So here, this is converging to this. So this sequence should converge to this, and that would never happen because every sequence is 0. Sequence of 0 converges to 0. It can never be equal to 1 by n.
Right.
Right? But
Right.
f of a plus root 2 by n
Yes.
is actually 0. It does not converges to 1 by n for any n belongs to it.
Yeah.
Okay. So this would be, therefore, function is not continuous at any rational point.
Yes.
So like for now, you don't know what would be the answer. Like you will start with the irrational part, same as that B belongs to irrationals,
Yes.
right? Then you'll write a function. What would be the function? Then 10 to the power n minus 1 B upon 10 to the power n minus 1. This converges to B.
Yes.
This is all the rational and this is all the irrational. But
Yes.
then this belongs to this. And see, here is the problem. You can't tell me the value of this. Achha,
Yes.
for you, what would be the value? Like, see, I know what is the value for m by n. It is?
Yes.
It is 1 by n. So what would be the value here? For f of m by n, my value is 1 by n. So here it would
Yeah. Not sure.
Sorry.
I'm not sure.
See, this is like an obvious guess is like this is P and this is integer, right? Greatest integer,
Yes.
the answer of the greatest integer, the range of the greatest integer is always an integer.
Yes.
And this is a natural number.
Yes.
So this is basically a P by Q form. This is a rational number.
Yes.
So
Yes.
the answer has to be 1 by 10 to the power n minus 1.
Yes. Yeah.
This is the obvious guess, right?
Yeah.
But I'm telling you this is wrong. You tell me a reason why this is wrong. I can't write it like that. There is a flaw here. The flaw is basically in the definition of m by n. The definition of m by n contained 4 points. One of the point was it is 1 by n even only when the GCD is 1. We don't know about the GCD here. Remember,
Yes.
we obtained 3 1 by 4 upon 100. GCD is not 1. I cannot write f of this is 1 by 100.
Yes.
Okay, so the GCD creates a problem here, and this usual way of proving the not continuity wala part is not going to work here.
Yes.
Okay, so we are doing it in the similar manner, but we are stuck somewhere, so we need to find some another approach.
Right.
Okay, so this is not gonna work.
Yes.
Let me just write it. This is not the part of my proof. This is actually where we got stuck. Okay. Now,
Right.
what is my another approach? Archimedean property. Heard about it?
I've heard about it. Yes. The Archimedean property. Yeah.
I think the spelling is wrong. I just do take care. I don't know. It is M.E. I guess.
That. Your screen. But yeah, this is correct.
Okay, whatever. Okay, the Archimedean property.
Yeah.
It says, let A belongs to real number.
Yes.
So, and A belongs to positive real number.
Yeah.
A belongs to positive real number, and B belongs to any real number.
Right.
Right.
Yeah.
Then there must exist a natural number n such that if you multiply your n with A, it would be greater than B.
Yes. Yes.
See, there can be two cases right now. A is here, B is here.
Yeah.
Right? And the other one is A is on this side, B is on this side. If A is already on this side, I can just multiply it by 1, and this is greater than B.
B, yeah.
Right? So I have found a n, there exists one n. So I have found a n, and that is equals to 1.
Yeah.
Yeah. So it says the other way around, like even if A is smaller, the only thing required is A has to be greater than 0.
Yes.
Okay. Here also A has to be greater than 0, not the B. So if A is greater than 0 and B is greater than A, so B is already greater than 0. Both are positive?
Yeah. Both are positive.
Now, there must exist an n such that NA will reach here, the B will be smaller, NA will be greater. Okay?
Right.
What Archimedean property says? We will use this we actually use this Archimedean property in so many times, but actually we don't use this word over there, so we get confused like how. For So the basic line that is always there in a proof, like let epsilon
Mhm.
greater than 0, then
Right.
epsilon greater than 0, then there exists a n belongs to natural such that 1 by n is less than epsilon. You tell me,
Right.
oh, I'm telling you this line uses the Archimedean property. You tell me what is A, B, N here.
Maybe an n here. N will be a natural numbers.
So N is actually N naught.
Yeah, yeah. We can take
N
N
is
naught. Yeah.
actually N naught. Yeah. What is A and what is B?
A and B will also be natural numbers between 0 and n naught.
No, 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 no. Acha, see this line. Do you agree with this line like this? Yes, this will happen.
Let epsilon greater than 0, then for every epsilon n naught belonging to natural numbers,
Such that
yeah, such that 1 by n naught is lesser than epsilon. Yes, no, wait, it won't be for
it won't be for.
every natural number.
No, it
For
won't be for
every
every
n naught
natural
belonging
number.
to n.
But yeah, that's why I've written not for every. There exist.
Yeah.
So
So will there exist one such at least? Yes.
yeah, and after that, every natural number will satisfy this property. If
Right.
let's say you have chosen a natural number 86, like for 86 it is true. So I'm saying for every natural number above 86 it will be true. 1 by 87, 1 by 88, 1 by 89 will be less than epsilon.
Right.
Right. So
Right.
for that,
That's
let's say what do we have here? Second, yeah. So what we can do here? Acha, so this is an intuitive idea, right? This is an intuitive idea. If we have to write it, like if I want you to show this actually. I'm also telling you that use the Archimedean property.
okay.
Okay, so the question is prove that for all epsilon greater than 0, there exists a n naught belongs to natural such that 1 by n naught is less than epsilon using Archimedean property. Archimedean property of reals, APR. So how will you do that?
Right. You can
see nothing you have to do. Just
Archimedean property.
Achha, what it says, A has to be.
Hello?
Yeah, what it says.
Your voice was breaking.
Yeah, what it says, A has to be positive.
A has to be positive, greater than 0. Yes.
So here, that A can be replaced by epsilon.
Yes, we can.
We can. So in APR, in place of A, I'll use epsilon.
Yeah.
Okay. B
Yes.
is any real number. Can I take B is equal to 1? Any real number?
So, 1.
There's no, at least there's no like problem in taking, because the Archimedean property says B can be any real number. So I've just taken 1.
But then B also has to be greater than 0. That is if it's the first line that we are considering.
Yeah, it means it can be greater than 0 or less than 1, greater than 0.
Sorry, greater than A. Sorry.
Oh, yeah, here. Yeah, yes.
Yeah.
Greater than 1. Yes.
Yeah.
Okay. So
it can be 1, yes.
Yeah, it can be 1. So let A is equal to epsilon, which is greater than 0, and
yes,
B equals to 1, that belongs to real.
Yes.
By Archimedean property, there exists n. There exists a n. So I'm saying there exists a n naught. There is a just difference of the notations. Okay.
Yeah.
there exists a n naught belongs to natural such that A times n naught will be greater than B.
Yes.
A is epsilon, n naught is n naught, B is 1. It implies n naught, no, it implies epsilon is greater than 1 by n naught, which implies 1 by n naught is less than epsilon.
Right.
See how we use the Archimedean property to actually prove this.
Right.
This
It's
is
still
not,
the
yeah.
theory application that I still need to revise more.
Yeah.
I mean, the property itself is clear, just the application of the theory to prove.
Yeah, exactly. How we are using, and we'll just use this line as such in the theorems. We won't write APR, but we should write. It's not like,
right.
Yeah, it should not like whenever you write for this, there existed this. What is the reason? Who gave you this guarantee that there existed? You can't say that I'll draw a line. See this epsilon is here, so I can always find an n such that it will be here. You can't give an intuitive idea in the proof.
Right.
Why? I have told you in the very beginning, because intuition works in R1, R2, R3. It would not be, extended to your R4, R5. We have to talk about the higher dimensions also.
Right.
So when we are in R, this is our edge actually. R is a very simple, like topologically, the topology that we discuss in real numbers, that is very simple, because every time we are allowed to just picturize it. Right. So I'm going to use the Archimedean property to actually prove that this function is not is continuous. Actually, is continuous on every irrational number.
Right.
Okay. It is not continuous on every rational, that I have proved here. In this one.
Right.
Page is finished. Let me start the another page here. Actually, one more thing. There are infinite number of rational in any neighborhood.
Yes.
There are infinite number of rational. Yes, that is true.
Yeah.
Let's say I'm taking let's say I'm taking b minus 1 to b plus 1. So this is my b and this distance is 1.
Yes.
Okay. So there will be infinite rational number here.
Yes.
Acha, what would you say if I restrict the denominator? I'm saying that you cannot use the denominator of a rational number greater than 3.
Okay.
Okay. So
there will still be infinite possibilities, right?
No.
Okay.
No. Just think about it. It's a the thought process is a very beautiful thing in this one. So I just want you to struggle in this. Okay. So you take an example. Start with an example. 2-3 examples. Like you take a number, let's say 0, not 0, 1.
Yes.
1. So from 0 to let's say 2 to 0 to 2.
Yes.
0 to 2 would be again thing here. Let's start with 0 to 1. This is my 0.5 and this is my 1.
Yes.
Okay.
Yes.
So of course, there's no doubt there are infinite irrational. But now I'm restricted. Yes. I have restricted your denominator. It will automatically restrict your numerator. Why? Because within this interval, you know that numerator will be always less than denominator.
Yes.
And I'm telling you denominator cannot exceed 3. So numerator is also restricted here.
Yes.
right? So if I'm telling you denominator has to be less than 1, so less than 3, so you have the choice of the denominator as 1 and 2, because the denominator is a natural number, remember?
Yes.
P by Q. P is an
Yes.
integer and this is a natural number. So, so there are two options. D can be 1, D can be 2. If D is
Yes.
1, if D is 1, I cannot have any option for the numerator.
Right.
Cannot put any integer here. If you'll put 0 here, 0 is not in this domain, in this interval. I've excluded my 0.
Right.
Okay.
Yeah.
The next number would be 1. It's also not there.
Yes.
Again, minus wala, you cannot, because then it would be here. Okay.
Yes.
For 2, what are the options that you have? 1 by 2 you have?
Yes.
Only 1 by 2. Only 1 by 2.
Yes.
So if I'm telling you that find all the rational number in this neighborhood whose denominator is less than 3, you'll say only one number is there, 1 by 2.
Yes.
Okay. So with this, we are ready to prove this one. Let function, I'm going to write function again here. Function was 0 for x irrational, and for m by n, that is rational, this is 1 by n. So let b is irrational. Let epsilon greater than 0 be given by then by Archimedean property. There exists a n naught belongs to natural such that 1 by n naught is less than epsilon.
Yes.
Okay. Now, there are only finite number of rationals with denominator less than this n naught that we have chosen in the interval b minus 1 to b plus 1.
Yes.
Okay. Every line has a sense for you. Every line
Yes.
has a reason for you, right?
Yes.
No.
Yes.
Acha. See, this is my b and this is my b minus 1, b plus 1. And what I'm saying is that there are finite numbers whose denominator is less than n naught, which means I can actually plot them and I can actually find a neighborhood in which no rational number with denominator less than n naught would be there.
Right.
Because they are finite, right? I can always, so what I'll do is, like, they are finite now. So this is the first rational number, this is the second one, this is the fourth one, this is the third one, this is the seventh one, this is the 100th one. Okay, so so I'm making one here, 101. It has to stop somewhere because it is finite, right?
Yes.
So I will take the distance of b from every rational number.
Yes.
And I'll take the minimum distance and I'll make a neighborhood within that distance. So no rational number would be in that neighborhood.
Yes.
We can choose a delta greater than 0 such that b minus delta and b plus delta doesn't contain any rational number whose denominator is less than n naught, because they were finite and we have excluded everything.
Yes.
Right. So it implies if I take any x within that neighborhood, if I take any, so what I'm doing is, this is my b minus delta, b plus delta. I'm taking x minus b less than delta. Okay, so I'm taking x minus. We have, tell me about f of x minus f of beta. What is your x? X is in between this interval.
In this interval, yeah.
Right.
Yeah.
It can be any rational number. It can be any irrational number.
Mhm.
Right. I cannot like give a definite value to it.
Yeah.
I don't know about x, but I know about b.
Mhm.
0.
Yes.
So this is nothing but f of x mod.
Yes.
Again, this
Yeah.
is again f of x naught is less than equal to 1 by n naught.
Yes.
This is less than epsilon.
Yes.
So what I have done, I have, first of all, I had an epsilon.
Yes.
I have made a delta. I have chosen a delta such that for every x here, my f of x minus f of b is less than epsilon. I've basically used the definition to prove that the function is continuous at all irrational.
Yes.
So you must know when to use the sequential criteria, and you should also know when I cannot proceed further. Now you need a
Yes.
whole new story. See, definitions will never let you down. Means if you're using the definitions, it may happen, it can, you don't know the approach, how to use the definitions, but definitions will always prove or disprove whatever is needed. Okay. All the other things,
Yes.
sequential criteria and everything, they're just, they're property. They're like a property. They are actually induced from the definitions. So
Right.
when nothing is working, try to use like, how can I make, how can I make use of definition in this question?
Yeah.
Okay. So if you have some, if you'll have any doubts in some sequential criteria question, you can just send me. I'll help you with that. Okay.
Yeah. Sure.
Yeah, actually I have a class, so I have to go now.
Oh, okay. 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 That's okay.
Okay. Acha,
That's
one more thing. I cannot give you classes like after Saturday. Like from Saturday, I cannot be available.
Oh, okay. That's fine. Today is Wednesday, right?
Yeah.
You can give classes to me on Friday and Saturday.
No, Saturday won't be possible. That's what I'm saying.
Okay, then tomorrow and the day after.
Yeah. So you can do
tomorrow.
it tomorrow and the day after. Okay.
Yeah, what timings will you be available? We can do it in the morning. That will be
No. I